Hello everybody. This episode is about using queries to formalize what a win and what a lose position is in a game. So we define a game to be a sequence of moves from one position, so one state of the game, to another position, to the new state of the game. So this is the very simple definition of a game. The more positions you have and the more moves are possible between positions, the more complex the game is. So the chess game has an enormous number of possible states and positions. We are going to use that for defining this win and lose position. So let's define what a win position is. So a win position is a position such that there is existing a position y that you can move from this win position to the other position y, and y is not a win position. Yeah, so this is a remarkably simple definition of a win position. It's actually derived from a paper from Weidong Chen and David Scott Warren, and I include the sources and the reference in the links below. Yeah, so this is what a win position is. You can now define what a lose position is. That's just the complement of a win position. So any position that is not a win position is a lose position. Let's have a look at the definition of a win position again. So win is defined in terms of itself. So something is a win position if something else is not a win position. This is recursion, a recursive definition, win defined in terms of win, and it's recursion over negation. So this predicate, not y in win, is a negated predicate. And recall episode number 9, where we had this barber example that was also having this feature. Then in this episode we will discuss that whether or not such a definition can be used to analyze a game. So let's tell this. So that's not a problem. Let's define the module game 1, just for our first game, and select this module game 1 and define our first game. That's a very artificial one, also taken from the paper by Chen and Warren. It has 3 positions. Position A, and you can move to A itself, which is a cycle, or to B. And B is another position, and from B you can move to C. And then you have the position C, and you cannot move to anywhere from C. Now recall the definition of win. From position C, we cannot move to any other position Y. So there doesn't exist such a Y. So C will not be a win position. So C will be a lose position. Yeah, and then B obviously would be a win position. But what about A? So A, you could cycle within A forever. And it's kind of undecided whether A is a win or a lose position. Let's tell this and ask for the win position. And then actually only B is found as a win position, but there's an error message here. So the status of position A is unclear, whether it's a win position or a lose position. So to show that it's a win position, we also would have to assume that it's a lose position, and that's paradoxical. If we display this in the graph editor, let's start with A. Then can show the outgoing attributes of that. So you can move from A to A, but also to B. And you can move from B to C. You can also graphically analyze what's a win position is. So it's instance of win, and this is instance of lose. And for that, we don't know whether it's win or lose. So the underlying game here is cyclic. And that causes the problem with the determining whether A is a win or a lose position. So the question now is, if we would have a game that is not cyclic, can we then use our very simple definition of win and lose to analyze the game for win and lose positions? And let's do that. So go back to the home module and define a new submodule game2, another game. Let's tell this and go to this module, game2. Now the game that I'm going to define here is a simple version of the NIM game. You have 13 chips and 2 players, and you can take 1, 2, or 3 chips in one move. And the player who is confronted with 0 chips is a loser. So you cannot do anything from the empty set of chips. So the definition of the game is very simple. Here done with rules. So here the positions are integer numbers between 0 and 13. So first rule says that 0 is a position, and this says that any number smaller or equal than 13 is also a position. So P1 is 1 plus an existing position, and the rule says we stop here with P smaller than 13, but then still 13 will be a position. The next 3 rules say what moves are possible. So you can take 1, 2, or 3 chips. And that's all. That's the whole definition of the NIM game. I tell that. And now let's ask the same query. So what are let's ask what are the lose positions? And it exactly finds the lose position. So 0 is a lose position, like with our position C, where there's no move possible from 0. But 4 is also a lose position, because the player that has 4 can only take between 1 and 3, and then the next player, the winner, would take the remainder, which would end up with the position 0. And likewise 8 and 12, so multiples of 4. then ask for the win position, and then it will give all the other positions in some order. These are the win position. So this game is not cyclic, and the very simple definition of win and lose gives you the win strategy for this game, namely putting the opponent into multiples of 4. And that's quite surprising that this simple rule can give you this strategy. Yeah, so that's the win game, the NIM game. Large games probably cannot be analyzed with this simple query just because of the complexity of the processing. So the chess game has cycles in it, complicated cycles in it, and so that is very hard to represent explicitly as a number of possible moves between states in the chess game. But still, small games can be analyzed by this very simple definition. And that was our little experiment in using such a non-stratified definition of a query like win to effectively analyze a non-cyclic game. Thank you for watching, and see you next time.